In this video, we will be looking at a more complex kinematics problem. In an action-adventure film, the hero is supposed to throw a grenade from his car, which is going 90 kilometers per hour, to his enemy's car, which is going 110 kilometers per hour. The enemy's car is 15.8 meters in front of the hero's when he lets go of the grenade. So far in the problem, we can see there's going to be two cars, and the hero will throw a grenade at the villain's car at some certain angle, and it has to land at the villain's car at this same exact point. So if the hero throws the grenade so its initial velocity relative to him is at an angle 45 degrees above the horizontal, what should the magnitude of the initial velocity be? So how fast does this grenade have to go at that angle for it to hit the car? So we need to find a lot of different things that will tell us or help us solve this problem, such as the time it takes for this grenade to travel from here to there, and where the car would be at that time. So obviously we have to ignore air resistance. If we decide to solve this problem with air resistance, we will never solve it. And before we get into the problem, here's some quick notes here, because traditionally we like to have things in meters per second, not really kilometers per hour. And there's obviously a distance here that I didn't really include, but the point is still here. The notation over here is just how the enemy observes the hero car. No, sorry, not the enemy, the Earth. How the Earth observes the hero car, which is 25 meters per second, and how the Earth observes the villain car, which is 30.56 meters per second. A little faster, but not too much faster. Actually, a lot faster, but it shouldn't matter. They're different. They have to be different speeds, or they don't have to be, but yeah, you get the point. So before we dive into this problem, let's go over some notes on relativity. So if you look at these equations over here, let's focus on the first one. So if we pay close attention to the subscripts, y over z plus z over w equals y over w, you can kind of remember this from simple algebra. And if you notice that you look at the subscript in your answer, it's actually just cancellation. It reminds you of cancellation. But this is just notation, so it's not actual math. You would just treat it like you're canceling terms, and that it's not multiplication, but it's plus. And the same thing applies over here, except you would flip the subscript of your second term, and you would have a minus here. So they're kind of just saying the same thing. It's just this one's plus, this one's minus, and this one's flipped. And this might be hard to understand at first because formulaically relativity is not that simple to understand, but let's look at an analogy that will hopefully make things clear. So let's say there's a robber over here, and let's say there's money over here. Let's assume the money grows legs and runs away from the robber at a faster speed. So let's ask the question, how fast does Mr. Beast or the robber see the money going? And we can actually just kind of use common sense and say that, oh, it has to be the speed of this minus the speed of this, because the speed of what Mr. Beast is going is going to be canceled out by the speed that the money is going, or that portion of the speed the money's going, and the remaining amount of speed that the money is also going will just be the sole amount of speed that Mr. Beast sees. Now, if this is too confusing of an explanation, we could always look at the notation. So, like I've mentioned earlier, it's just simply the velocity of the money relative to the Earth, observed by the Earth, minus the velocity of Mr. Beast as observed by the Earth, which kind of just means this one over here. And if you want to simplify it back to this term over here, all we have to do is just swap the subscript of the second term, which would be the Mr. Beast one, and obviously just have the plus sign, so we will just put the plus sign. And if we do term cancellation, it will just be the velocity of the money as observed by Mr. Beast. So yeah, this is the answer of this is literally just the velocity of the money minus the velocity of Mr. Speed, or Mr. Beast, not Mr. Speed, sorry. Okay, let's actually go into the problem where we actually utilize this and put this into practice. Let's say we have a hero that goes a certain speed, as observed by the Earth, and he throws the grenade. So that's the velocity of the grenade as observed by the hero, not the Earth. This term would be slower, or not slower. It would be horizontally faster if it was observed by the Earth. But for simplicity's sake, I want to keep everything observed by the hero, because if I have everything observed by the Earth, you will run into a situation where you get your answer that completely neglects the speed of the hero. And we don't want that. I want to just have just a grenade thrown and the speed observed by the hero. So let's actually take a look at that. We have a distance d that the situation starts initially, and we have a villain. And this villain is going a speed as well, as observed by the Earth. And let's include the angle theta. Now, in this problem, we're going to bring up a vector equation. If you're familiar with vectors, they're usually written in angled brackets, and the first part, or before the comma, is going to be the x, the horizontal component, and the y part, the second part after the comma, is going to be the vertical component. So let's take a look at this. Over here, this is actually how the hero observes the villain. So this is how Deku over here observes Dabi going a certain speed. If you don't know who these are, just pretend this is a good guy, this is a bad guy. So this equation over here represents how the hero observes the villain over here. So, like we mentioned before earlier, remember how the velocity of the velocity of the money minus the velocity of Mr. Beast gives you the observed velocity of the money by Mr. Beast. So this is actually just the same concept here. Over here we have the Earth observing the villain, so just the velocity of the villain minus the velocity of the hero of as observed by the Earth, and that just gives you the velocity of how the hero observes the villain. So that's actually going to be useful for us. In this case, what you can actually do is just imagine that all this stupid observance velocities just gets stationary, and you have the remaining velocity, which is just this velocity. That's the only velocity that's moving, plus the distance d, and obviously the y component would just be 0 because none of them are flying. Only the grenade is flying, nothing else. So we can actually pretend this is the speed that the villain is going, and everything else is still before the grenade is thrown, obviously. And we would need to have a vector equation for the grenade as observed by the hero as well, because the two things interacting are the villain and the grenade. So we want both of them to be observed by the hero. So let's go with that. So this is the grenade as observed by the hero. You have the x component of velocity times t, which should be familiar to you by now. If not, this is just the constant speed equation for position horizontally. So you have v initial t plus x initial. Obviously, the grenade starts exactly where the hero is, which we coin as 0. So I just didn't put that in there. And this is obviously the velocity as observed, or how the hero observes the velocity of the grenade. And cosine theta, that just means the x component. And the y component, this should be familiar too. Obviously, when you throw the grenade, there's going to be gravity, and gravity is going to act downwards, or gravity is the acceleration acting downward. So we need to include that g over 2t squared. That negative means downward because we define negative as downward. So that would make sense in our problem. That way we don't get a negative time. Please include a negative here. And right, same thing as discussed. This is just the vertical component t plus y initial. Y initial is just going to be 0. So in this problem, what is really happening? We need to ask this question. What's really happening? So what's happening is we want this vector quantity over here to equal this vector quantity here. X component of this equals the x component of that. Y component of this equals the y component of that. So you might ask, Why do they have to be? What does that mean? Why do we have to make them equal? Well, if you understand this properly, the hero's throwing a grenade, and we want the horizontal position of this grenade to equal the horizontal position of the villain. That's going to take a certain amount of time to do so, because obviously the grenade has to go faster for this to happen. So we're actually solving for time over here if we have to piece together an equal scenario. So let's go ahead and do that. Over here, I set the x component of the villain equal to the x component of the grenade. So I actually want to find a time where the horizontal positions are equal. That means, what time will this grenade catch up to this villain horizontally? Let's look at obviously the vertical part needs to match too, but we need to solve for the time first. So the time will give us more information. We can just put the time back into the vertical one. That will just tell us how far each has traveled. The villain will just stay at 0, so it doesn't really matter. But how far the grenade has traveled. Now, let's solve for the time here. Let's subtract this component over here to the other side. Let's factor out a t and divide what's inside the factor over to the other side, and that's our t. It's actually just basic algebra. You can use numbers if you want. I'd like to do stuff symbolically because I feel like rounding can become an issue when there's too many numbers. So this is just our t equals that. So this is our time. So we're gonna have to use this time. This is the time it takes for the grenade to horizontally catch up to the villain car. Now, we want this time so that we want to observe how the vertical trajectory of the grenade acts. So we would actually want to plug this time in here into the pluggable equation and set that equal to this component here. The vertical positions need to equal within this amount of time. Now, this is going to be really complicated to do. Obviously, please do not use the quadratic formula. It's going to be very hard. And if you can, very good. But you can take advantage of Desmos or a graphing calculator. And I'll show you in just a bit what that would look like. Now, let's go ahead and plug it back in to the Desmos.